Okay, hello everybody. So as some of you who follow our seminar know, my talk on basic constructions in quasi-categories, which was about 2 or 3 weeks ago, it wasn't recorded for some technical issues. I don't know what happened. So this video is supposed to fill the gap in our seminar series and yes, and this will be a replacement talk for this recording, for this missing recording. So the topic, which wasn't recorded, are basic constructions in quasi-categories. And by the way, I should say that in this talk, I will follow Moritz Groth notes, a short course of infinity categories. I suppose this is the name. So first, let me recall when we stopped on the last talk. So firstly, what is a quasi-category? So a quasi-category is a simple shell set C such that every inner horn so inner means that this horn is between 0 and n, can be extended to the full simplex. So this is the definition of quasi-category we covered in the previous talk. So if we have a quasi-category, how we think about it in kind of categorical terms. So we have objects. This will be just vertices of our simple shell set. And morphisms. So a morphism from X to Y, from object X to object Y, is a one simplex F such that D0 of F is equal to Y and D1 of F is equal to X. However, the whole idea of quasi-categories and infinity categories that we not only have one morphisms, we actually have two morphisms and morphisms for every n. So what will be two morphisms in our category? So this will be homotopies between morphisms. So what is homotopy? If we have two morphisms, f and g, from x to y, we say that they are homotopic if we have the following simplex and this triangle can be filled to a simplex. So homotopy between f and g is this simplex sigma here. And this gives us an idea what are two morphisms from x to y. Actually, we have morphisms for every n. So what would be an n morphism? So an n morphism from x to y, this will be an n simplex sigma such that dn of sigma is equal to x. So here I'm I'm abbreviating the notation, because really what I mean by dn sigma of is equal to x is that dn sigma is equal to the appropriate degeneracy of x. Okay, so in particular, I have a n simplex. I'm removing one vertex. I have a face opposite to this vertex, and all of vertices in this face are equal to x. All edges are equal to identity of x, and so on and so forth. And d0 up to dn minus 1 of sigma is equal to y. So it is this is an morphism. What does it mean? So as I said, opposed to nth vertex, I have a face consisting only of x's and identities on x, and so on and so forth, and the one remaining vertex is equal to y. And we can actually assemble all of these morphisms to a space of morphisms, which actually turns out to be a Kan complex. So what we did in the last talk, in the previous talk, was also defining a homotopy category. So what is a homotopy category of an infinity category? So homotopy category of a quasi-category is an ordinary category with objects equal to vertices of our quasi-category and morphisms the homotopy classes of morphisms in C. And the composition is given by G and F. Composed is just the class of G composed with F. So here I need to make one more remark. Homotopy defines as an equivalence relation on set of morphisms from object X to object Y. This is also what we discussed in previous talk, and this is what we are doing here. Okay, so now let's go to actual content of the current talk. So first we will discuss what will be functors of quasi-categories. And here the definition is rather easy. So we actually can define a functor to a quasi-category from any simplicial set. So let K be a simplicial set, and let C be a quasi-category. Then a functor F from K to C is just a map of simplicial sets. And we actually have, similarly as we have a space of maps in a quasi-category, we have actually whole space of functors. From K to C, which is given by functors from K to C. So this is supposed to be a simplicial set. So I will put this bullet over here, and this is equal to morphisms in simplicial sets of bullet simplex times K to C. And this whole space of functors is, of course, a simplicial set. So zero, yes, so vertices of this space are functors between K and C, but we have also natural transformations existing in this space. So in particular, the one simplices in our space are natural transformations. And what is the idea behind functors in quasi-categories? So the idea is that functors of, in general, infinity categories, because quasi-categories are supposed to be a model for infinity one categories. So functors of infinity categories are functors up to what is called coherent homotopy. So let's see how does it work on an example. And as an example, let's take some category. And let F be a quasi-category functor from the nerf of A to C, where C is some quasi-category. So this was supposed to be a functor of quasi-categories. Okay, so this functor is taking objects, so vertices to vertices, arrows to arrows, so that's fine. But now we know that in quasi-category, we cannot really compose morphisms. Rather, we are composing, when we are composing two morphisms, there might be plenty of compositions, but all of the choices are homotopic. However, let's see what is happening here when we are composing two morphisms in A. So when we are composing two morphisms in A, we have the following two simplex in the nerf of A. And this will be sent by F to the following simplex. So here we have F of F. Here we have F of G, but also we are choosing one of possible compositions for F of F and F of G. So here we'll have F of F composed with G. Sorry, F of G composed with F. And moreover, what we did is we chosen a witness of this composition, but also we have chosen a coherence. We have chosen um, a witness of this composition and also via which two simplex this witness is achieved. And also the choices of witnesses are coherent up to coherent homotopy. So let's see what does it mean. So now let's take three morphism in, three simplex in the nerve of A. And what it will be sent to, well, so here we'll have three simplex. So just give me a moment to draw it. Okay, so what we have on the bottom face of this three simplex, so this, maybe I will change the color. This is f of f. This is f of g. And so in the bottom simplex, what we have, this is a witness of f of g composed with f. However, we want also to compose all of this stuff with h. So this edge over here will be f of h. Now, over here, we have a two simplex, which will find a witness for composing f of g and f of h. So this edge over here, this will be f of h composed with g. Now we have bottom simplex, we have rightmost simplex. So now let's look on the leftmost simplex. So over here on this edge, we have f of f, and on this edge we have f of h composed with g. So what we'll have over here is f of h composed with g composed with f. And because this whole three simplex will be filled, all of the choices which we made are coherent up to coherent homotopy. So this is the idea. And so on and so forth for higher simplices. And later on, when we'll discuss on this seminar simplicial categories, this will turn out. So now what we are talking about are kind of witnesses and choices of witnesses, but when we will discuss simplicial categories, this will actually turn out to be coherent choice of homotopies between compositions and stuff like this. Okay. Now, if we have usual categories A and B, then functors from A to B form a category yes, so let's write as functors from A to B. And moreover, if we have equivalent categories A equivalent to A prime and B equivalent to B prime, then the functors categories are also equivalent. So, of course, we would like to have something similar in the quasi-categorical setting, and we indeed have. So this is a proposition. that let sorry, yes, let C and D be uh, infinity categories, and let K and L be simplicial sets. So then firstly, the simplicial set functors from K to C is also an infinity category. Secondly, if C goes to D is an equivalence of infinity categories, then also the induced map is an equivalence of infinity categories. So let me stop here because the third point of this proposition would use a notion of categorical equivalence, and we haven't discussed it yet on this seminar. Yes, I should also say here that in general in this seminar we are not proving anything. So if you are interested on the proof or on the details, I encourage you to take a look on the source. Okay, now let's start our journey towards limits and colimits. So firstly, we'll start with a kind of supplementary construction for all of this. So this is a joint construction. So joint construction in topological spaces is something rather well known. So if we have two spaces, A and B, then join of these two spaces are is the space where all points of A are connected by a path to, sorry, every point of A is connected by a path to every point of B. So we get something like this. Yes, exactly. So we can also have such a construction for categories. How does it work? So given categories A and B, and here, of course, by categories, I mean ordinary categories, the join A and B is the category with objects. So the class of objects of the join is a disjoint union of objects of A and objects of B. And the morphisms. So if we have morphisms in the join between two objects X and Y, so we have four possible cases. Firstly, if X and Y are both in A, then the morphisms between X and Y in the join will be equal to the morphism in the category A between objects X and Y. Ditto for B. However, there is a single morphism if X belongs to A and Y belongs to B. And there is no morphisms if X belongs to B and Y belongs to A. So really what we are doing here is we are mimicking the construction of the join in topological spaces. So we have two categories. We can think, for example, about them as one on the bottom, one on the top. And firstly, of course, if we have objects on the bottom, then morphisms, two objects on the bottom, then morphisms between them are morphisms on the bottom. Same for the top. But if we have an object on the bottom and an object on the top, then morphism from the bottom to the top consists of one single morphism. And we cannot go down from the top to the bottom. Yes. So in particular, it is important here that this construction is not symmetric. Okay, a couple of examples of this construction. So for example, if we have any category and we have B to be a category consisting of one point, just one object, then A defined as A join with B is called the right cone or cocone on A. On the other hand, once again, if we have A to be a category consisting of one point and B any category, then B yes is equal to A join B. So this is the left cone or cone on B. In particular, the first one is relevant for the study of colimits, and the second one is relevant for the study of limits. And in particular, yes, for example, if we have a category which is consisting of three objects and two arrows looking like this. So this is the category which is describing pushouts. Then its cocone will look as follows. And if we want to generalize this idea to quasi-categories, what we need to do is to look for a joint construction in simplicial sets. And this construction can be extended. And we kind of have already an idea how to extend this construction. So if we have, for example, two zero simplices, one in K and one in L, we know that in the join, there should be connected by one simplex. K join L. And if we have, for example, zero simplex in K, and here I should write belonging, and one simplex in L, then there should be connected by a two simplex in K join L. So the definition is that if we have two simplicial sets, then the join K join L is the simplicial set given by so n simplices of K join L consists of n simplices of K with K simplices n simplices of L and a sum of I plus 1 plus j equal to n of Ki cross Lj. And so these are only the simplices, and it's rather easy to write the degeneracies and phase maps, so we will not do it here. And in particular, what we have, this construction comes with canonical inclusions of K to K join L and of L to K join L. Okay, and this construction, this join construction can be actually described and characterized by the following two properties. Yes. So firstly, the partial join functor so by partial join, we mean that we are making join with K, and it is a factor on the second variable from simplicial sets to simplicial sets below K. And sorry. So these two factors are supposed to preserve colimits. And the second property is that for the standard simplices, we find that join of the ith standard simplex and j standard simplex is isomorphic to I plus j plus 1 standard simplex. And these isomorphisms are compatible with inclusions of delta I and delta j. So one of the things which I'm not really discussing here is that all of this construction which we are providing are coherent with categorical notions. In particular, if I have two categories, two ordinary categories, and I take join of their nerves, this will be isomorphic to the nerve of their join. Okay, and how the join construction works for quasi-categories. So it is a proposition. Firstly, if C and D are quasi-categories, then so is the join. Secondly, if F from C to C prime and G from D to D prime are equivalences of quasi-categories, then also join of these two functors F and G going from C join D to C prime join D prime, then also the join of this functor is an equivalence. Okay, and first thing to which we are going to use a join construction is the slice construction. So in the usual category theory, what is happening? So if we have a category B, and object X, then we can discuss an over category B over X. So this is a category which consists of objects are maps from X prime to X, and maps in the over category are maps of objects in B coherent with the maps going to X. So an over category is a generalization of a more, is a particular instance of a more general construction. So which is called the slice category. So generalization. So instead of a single object, which is just a functor from a one-point category to the category B, we can consider a functor, well, arbitrary functor from a category A to B. So we think about this P as a diagram. And this gives us a notion of slice category. B over P. So this is supposed to be an over category over the functor P. So what are the objects? So the objects are elements of are objects of the category B with a natural transformation from the constant diagram on the element B to the diagram P. So really, what is happening here is we are kind of mimicking the condition for the over category for a single object. But now what we are doing, well, we are kind of forming cones over the functor P. And what are the maps? So maps are, well, maps in the category B compatible with natural transformations. Okay, now there is natural bijection between a category of functors, sorry, between functors from the category C to the over category to the slice category over the functor P with functors over P from the category from the join of C and A and B. And let me explain the right-hand side. So on the right-hand side consists of all functors from C join A to B such that the following diagram commutes. So the diagram is, we have inclusion of A to the join of C and A, and then we have our functor. And here we have the functor P, and this diagram is supposed to be commuting. So I encourage you to analyze this natural bijection because it is a nice exercise to see how this joint construction works. And now we'll write it in a little bit more sophisticated way. So we write this bijection as the following thing. So as homomorphisms in the category of categories from C to the slice category over P, so this is in natural bijection with homomorphism in the under category of A from the object A to C join A to B. Now, this more sophisticated way is supposed to give us an idea how to define slice category in the infinity categorical context. So it is given by the following proposition. So let P from L to C be a map of simplicial sets with C being an infinity category, so a quasi-category. Then there is a quasi-category C over P characterized by the following universal property. Uh, so for every simplicial set K, there is a natural bijection between space of morphisms in simplicial sets from K to CP, so this is the object which we are defining, is isomorphic with the space of morphisms in the over category of L, sorry, under category of L, from L to K join L to L to C. So this one is really mimicking the condition in the ordinary categories. And we have actually more explicit description. So the infinity category C over P is the infinity category of cones over P. So its n simplices consists of homomorphisms in the category in the under category of L from L to delta n join L to L to C. So once again, we are going to kind of see this idea of homotopy coherent constructions. So let's see what is an over category for a single object. So example, let's take C to be an infinity category and X in C be an object. Characterized by the map Kx from theta 0 to C. Then the category X over K of X is the category, is the over category well over X. So what is an object? Object in this over category, so a vertex, is a map using this description above, the one over here, yes, we can actually write what is an object here. So an object is a map. So it is, oh, sorry. A join of two zero simplices, which is equal to one simplex, which is isomorphic to one simplex, such that its D0 is equal to X. So its target is equal to X. And what are maps in this category? Well, they are two simplices, so joins of one simplex with a zero simplex of this form. Okay, now we are in a position to define final and initial objects. So a definition, so an object X in infinity category C is a final object if the canonical map C over X to C is an acyclic vibrations is an acyclic vibration of simplicial sets. So this gives us well, what does it say is that if we remove the object X from the category C, then we don't lose any information. But we have also more explicit description of these final objects. So a proposition, the following conditions are equivalent. Firstly, the object X is final. Secondly, the mapping spaces so maps of C from X prime to X, so are acyclic Can complexes for all X prime in C. And the third condition is that every simplicial sphere in C can be filled, such that it finishes with X. This can be filled to an entire n simplex. So here in the second condition, we can see one of the ideas which occurs in the infinity categories. So if we have a final object in a usual category theory, then it is characterized by the property that from every object of our category, there exists a unique morphism to our final object. And here in a quasi-category setting or infinity category setting, we replace this condition by saying that instead of having one unique morphism, we have contractible space of morphisms. Okay, and there is also one thing I should say here. I will not write it, but also final object should be unique. And here in quasi-categorical setting, we once again have an idea that if we have a quasi-category spanned by final objects, so this will be a full subcategory. So this will be the subcategory of a quasi-category, full subcategory of a quasi-category will be spanned by some set of vertices, will consist of these simplices, which have all of the vertices in this given set. In particular, if this given set is the set of final objects, so we are choosing a subcategory such that all simplices have vertices as a final objects. So this full subcategory will be once again contractible Kan complex, or it will be empty. Okay, and now we are in a position to define limits and colimits. And here we'll stop on the definition of these objects. So a definition. So let K be a simplicial set and C be a quasi-category. So a colimit of a diagram P going from K to C. So this is an initial object in the category, under category for the functor P. And similarly, we say that yes, a limit of P from K to C, this would be a final object in the over category of the functor P. Okay, and I will stop here. So thank you very much for listening, and we'll come back to these ideas and explore them more in the upcoming talks. So thank you very much.